this is being recorded now at this point in time. Yeah. Okay, shut up. All right, 31 to 40. Do I still have any unfinished business here? Do I have any unfinished business? 36, 39, 40. Hang on. All right. Yep, I got a request for 36 here. 39, 40, right? 36, 39, 40. That was the. Okay. Yeah, I have some unfinished business here. Lah. Okay, let's do 36 first. All right, let's do 36. Okay, so I haven't done this in a while, right? Capacitance. So I will probably do it now as well. Hang on now. Okay, hang on, let me just check everything. Have everything. Okay, let's do this now. Okay. They're connected in series, so I want to remind you, battery, right? Capacitor, and then the 9-volt battery. So this is a factual thing, okay? So what happens is you need to understand that the Q, right? The Q overall is the same for both, right? Okay, so the amount of charge, right, stored in the capacitors, right, overall is the same for both, right? So it's a fact. You have to memorize this, right? To find the Q overall, you need to find the total capacitance, right? You need to find C total. So that's what we're gonna do. C total for series, right? So what's the C total for series? 1/3 micro plus 1/6 micro, and then inverse, right? That will be the total in series. How much is this? 2 microfarads in total. All right. So what we want to do is we want to use this to find Q total, Q overall. So Q overall would be CV, right? C times V. So that will be 2 micro times 9. That will make it 18 microcoulombs stored, right? And the idea is it's both the same amount, 18 microcoulombs here, 18 microcoulombs here, right? So you can try to understand this and explain why is it like that, but I think it's better that you remember this, like, you know, hardcore, right? Just memorize this, right? Because the you know, to explain this whole thing, right, it's gonna take very long. To explain this whole thing is gonna take very long. I can show you a clip for this one, but the very basic essential thing is this. When the current flows, right, at the start, when it's uncharged, when both capacitors are uncharged, when the current starts to flow, right, both capacitors will start to charge. When we talk about current flowing, we imagine the you know, the positive charges flowing, but it's not actually the positive charges, it's the negative charges that are flowing the other way, right? So there's the electrons flowing this way. So electrons are being accumulated on this side, all right? And then positive charges will accumulate on this side. Then electrons will accumulate on this side, and positive charges will accumulate on this side. So now, since they're in series, the amount of current flowing in every section should be the same, right? The amount of current flowing should be the same. So it's kind of like the I is the same, right? I equals to Q over T, right? I equals to Q over T. At some point, capacitors will get fully charged, right? With their respective voltages, right? Their respective voltage will be different, but once they are fully charged, and they will get fully charged at the same time, okay? They will all get, both capacitors will get fully charged in the same time. Since they would have been fully charged in the same amount of time, they get the same amount of current. They will have the same amount of charge stored, right, in both of them. Right, that's like the summary of the idea here. Okay, but yeah, that's how it works. So if they're in parallel, you got to remember that they are charged to the same voltage, right? They will get same total voltage. So if it's 9 volts, this one will be 9 volts, this one also will be 9 volts, right? They may end charging at different times. Maybe one of them will finish charging, the other one still is being charged, right? That means the current will only go to the other one. Yeah, so depends on the capacitance. No. The charge stop will be different. The voltage is the same. The charge is different. For this one here, the charge is the same. The voltage is different. Okay. It sounds like a resistor circuit. It sounds like a resistor circuit, right? Series is the same, so charge is the same. Parallel voltage is the same, but current is different. Yeah. No. It's same. It's the same. It's the same. Oh, I mean, calculation for capacitance look like the reverse, but yeah, I mean, capacitance and resistance two different things. Yeah. Okay, so this is this is capacitance one. Just very fast run through. But yeah, there you go. Right. I got request for 39 and 40. Okay. Half-life of radioactive nuclide is 8 seconds. Initial activity is 10,000 becquerels. What will be the approximate activity after 4 seconds? So you're supposed to do this without a calculator. So that's why it's hard, you see. Okay. So if you're thinking of trying to use A equals to A naught E negative lambda T, I would suggest you don't, because this is going to be really hard to understand. Unless you can do exponential calculations in your head. Don't try, Mateo. I know you try. Don't try. Okay. Right. So we have to think of the other method. What's the other method that I thought is half to the power of n? Yeah, half to the power of n. So we know that the initial activity is 10,000. Then times we are trying to find the current activity. Okay, and then times half to the power of half. Right, because 4 seconds is like half of 8 seconds, right? 4 seconds is half of 8 seconds, so it's a half-life. Huh? How would you square root? So I just try lah, just try. What? I don't know. I don't know yet. I'm gonna just 1 over root 2, isn't it? I mean, a square root 1 is 1. A square root. Hello. It's yeah, like, it's half a half-life. 4 out of 8 seconds is half a half-life, not 1/4. Oh no. Yeah. So you can work this out, and then what's root 2? Root 2 is about 1.4. About 1.4. Yeah. So unfortunately, these are some of the numbers they want you to memorize. Yeah. So 1.4. Yeah, 1.4. So 10,000 divided by 1.4. I have no idea. Should I do this 1.5? Does that help? No. So no. 3 over 2. Shut up. So does this help? 2 over 3 times 10,000. Huh? Oh my god, you mean the answer is not C? Oh shit, yeah, okay. Yeah, because D is like 3/4, right? Yeah, it's closer to 2/3. Yeah. So down here it's all approximate already. Yeah. So you're supposed to do this estimation. Are we okay on this? Oh, what the heck is 40, man? Wow. Oh shit. What? Huh? What's N? No, N is the number of half-lives that has passed. Small n? You're talking about small n? You're talking about small n here? This will be no. 40 del x of p. Number of half-lives.
This is the same, like 40 is so much.
What?
40 is
Wait, hang on. Yeah, I'll finish up C first. You okay? Yeah, basically it's half of 8 seconds, right? So it's half a half-life.
let's say they change it to 5.
Yeah, right. Yeah, that's right. Yeah, you're right. Like I could ask you this, dude. I can ask you, what's the activity after 16 seconds, for example? Come sit down. Happy birthday. Come. Happy birthday to you. Happy birthday to you.
Happy birthday to you. Now it's demo.
Wait, hang on. Do you all learn Tamil or do you learn Hindi? Tamil. Okay. No, I'm just checking. Like, yeah. Because Girin learns Hindi, right? Okay. Is there some division or line drawn or something like that? Oh, okay, okay. Well, he's being very politically correct. Yeah, he's being very politically correct. CB is being very PC, right? Yeah, okay. Brian, what happens if this is 16 seconds? Yeah, two half lives and n equals to 2, lah, right? So it will be your a equals to a. It will be your a is equals to a naught, like half to the power of 2, that sort of thing. Okay? Then it will become 1/4. Yeah, 1/4. Hey, hang on, I need to check my alignment, sorry. Hey, misaligned. One of your bags. The paper is gone. I had a piece of paper there. Not like a bit koyak. Yum, 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 yum. Hang on. Oh. I have to do some quick fix now. Okay.
What?
What? Okay, 40, 40. All right. So 40, 40, 40, 40, particle confined in nucleus. All right. What's the magnitude of uncertainty of the momentum? So based on this question, you're looking at del x, del p, right, is equals to h over 4 pi, right? Right, del x del p is equal to h over 4 pi, or rather you can say more equals to, doesn't really matter to me. Within the nucleus, so confined within the nucleus, so this is your del x. This tells you your uncertainty position, right? So your particle is in a nucleus, but we're not too sure where it is. Okay? So this one requires remember the size of a nucleus. That's minus 15. Atom is minus 10. This is a nucleus. So nucleus, you need to memorize this. This is something for you to memorize. Okay, what if you're like, oh no, I cannot, I need some confirmation. Like I don't really know whether is it 15 or 10. Maybe you panic. Look for Fermi's radius. In the data booklet lah. Look for Fermi's radius. Where is Fermi's radius? What? Yeah, there you go. So Fermi's radius, right now, the order is 10 to the power minus 15. So you got to remember what Fermi's radius, which equation is it being used in? Which equation?
R equals to R.
R equals to R naught, A to the power of 1/3, right? This equation here. So what was this equation used to do?
Find the estimated radius of snake.
Yeah, so nuclear radius, so radius of nucleus, okay? So you can see that it's R naught, which is 10 to the power minus 15 times to the power 1/3. So X is in the scale of 10 to the power minus 15, all right? So if you panic, you cannot remember, just remember Fermi helps you find the nucleus, right? Nucleus. But for atom, atomic size, all right, atom, yes, is 10 to the power minus 10 meters, okay? So remember that. Atom is 10 to the power minus 10, nucleus is 10 to the power minus 15, all right? So back to the question, okay? So nucleus 10 to the power minus 15, that's the order of it. So we just take this, find del P, right? Now, there's this, so the numbers are quite far apart. So I don't think I need to worry that much. But we know H is 10 to the power minus 34, right? And technically 4 pi is 4 times 3.14. Makes it close to 12, which makes it close to 10. So you know, for some questions, they even include this 10 inside. So technically speaking, you're looking for uncertainty of momentum will be 10 to the power minus 35 over 10 to the power minus 15. Right? Then that will be the answer, right? So C is the answer. Yes. No, I just want to remind you, right? So the 4 pi does give you a 1 factor down. The 4 pi does you know, drop the factor by 1. This IB.
This is the hard ones.
Yeah, of course. That's why I'm doing it.
But how the prelims of school going?
Because the prelims, the school ones, they try to test more on calculations and all that. Like, you know, they I think in a sense they cast a wide net to try to make sure that the next 6 weeks, right, you guys focus on how to use the data booklet equation. But they don't really test you on application. Yeah. And no, I mean it's kind of like it's good. It's good to push the entire population's grade up. Like, you know, to push the entire physics population grade up, maybe from a 5 to a 6. But if you want to go from 6 to 7, like, it's this kind of questions. You know what I mean? Yeah. So I mean that's the reason why we're doing all the past year papers, right? Otherwise I'll just teach only, right? Okay, let's do some paper 2. Let's do some paper 2. Right? We will definitely not be able to finish everything because I still need to go back to revision. All right, but there we go. We will just start on a few things. Yo, what the heck is this? Why is the first question like that? Wait, hang on. Oh, okay. So wait, what's the additional question you asked me on the chat? What was it about? Question 2. Okay, I'll get there lah. Okay. So unfortunately, this question, I mean, I'm assuming you already done it. So I'm just gonna jump in and tell you where's the most important point. The most important point of this question is actually this word here, the maximum speed. Yeah, this is like the key to the entire. This is the key to the entire paper, the entire question. The word maximum speed. What maximum speed means is that on the bicycle, right? Bicycle. Okay. All right. When she's at the maximum speed, right? Max speed. Okay, max speed. She has no what you call it? No acceleration, which also means that her driving force, electric driving force, is equals to the drag. Right? It's equals to the drag. Okay. Yes. No, dude. That's an e-scooter. This is the e-scooter. Yeah, it's an e-scooter. Yeah. What? What?
The blast
Oh, East Coast.
the whole of semester. The blast kind of
This is that specific song?
this quite from down.
Yeah. Oh my god. Okay, so there you go. Right. But those two parts doesn't rely on that. It's actually the next one, this one here. This part 3. Friction and resistance act on the bicycle and the girl when they move. Assume all energy is transferred from the battery to the motor. Determine the total average resistive force that acts on the bicycle and the girl. So this was the part where you need to understand this part here, right? This one is the one, right? This one here.
I think you just use E equals
Yeah, you can. Yeah, I mean that's it lah. Yeah, I mean it's P equals FV lah. But hang on, first two parts any questions though? First two okay No, it's not capacitance. It's not. Hey guys, don't get you. Hey, I had a lot of recent, like, you know, questions from on WhatsApp, and I realized that a lot of people are like, you know, they read the word discharge or they see the word battery, they think it's capacitance. It's not. It's not. It's capacitance when they tell you it's capacitance. Yeah. This just treat it as like a normal. Okay, but one thing that students always forget for electricity are these two equations. These two equations. Yeah, something like that, right? So a lot of times students forget about these two equations, right? In fact, I will also add on a variation of this equation, right? I equals to Q over T equals to NE over T, in case they want you to calculate the number of electrons. And I also want to remind you that there's also this equation, I equals NEVQ.
Isn't it the
Yeah.
something speed?
Drift speed, yeah. But I also want to remind you about this. I'm going to manipulate this V equals to the work done over charge, and I'm going to manipulate it to work done equals to Q times V. That's like energy. Energy equals to Q, right? Okay. Yeah. So for part 2, if you had to do the power output, then you have to take the total energy. Yeah, because you got V here, you got Q here. You can find the total energy and then divide it by time. Will be power, right? That will be power. No, that's not weird. What? Hey, hang on. Sorry, what? No. I mean, no. You can. Okay. No. You can. Hang on. You're talking about this, is it? You're talking about this equation. This equation is a capacitance equation, right? The problem with this equation though is that it's used for capacitors. That we don't have the capacitance of a battery here. Like they didn't tell us what's the capacitance. I guess what you're trying to say is, can I also use QV in a set of capacitance equations? And the answer is yes, you can. Yeah, but you can't use this equation here, right, for this question. What's that smell? What's that citrusy smell? Oh, okay. Ooh. All right. Anyway, hang on. I need to address the next one. Okay. So they're asking for the drag force. They're asking for the resistive force. But it is your understanding at maximum speed, the drag force is equals to the resistive, is equals to the driving force, right? F equals to FD, like this, right? So what you need to do is you can find the driving force, right? Find driving force. So the driving force can be found from P equals to FV. Right? Because you calculated power 240, you calculated they give you the speed, which is the whatever speed they give you there, and then you can find the force there. Right, this will be the driving force. Sorry, Eric, you were asking, how can they ask you about this one here, right? But yeah, I think yes, they can. Yeah, they can. Yeah, they totally can. That's the idea. In any case, question 1 is supposed to be a topic 2 question. So technically speaking, if you read everything, only part 2 is the one that's a bit off, right? Because part 2 they introduce topic 5. But yeah, this is topic 1, right? How long does it take to travel 20 km at this max speed? I think one thing that they should have emphasized in this, like you said, you were complaining about the language of this question, which I agree. They should have emphasized that this girl is traveling at max speed all the way. Right? It's traveling at this maximum speed all the way. Right? So that's the thing, right? But yeah.
Wait, but how does it affect
Part 2.
I use equals to find
Use P equals FV to find part 2.
yeah.
Use P equals to VI.
I found the
P equals to VI.
current.
So you went to take 16 multiplied by 43,000 coulombs divided by 3 times 10 to the power 3. You tried to do that and you didn't get the answer? Huh? Yeah. Wait, what?
The is it
No,
no right? You can
no, 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 no.
done equals to
Yeah. That's what I just said.
yeah no but my method is the unconventional way.
Oh no. I think that both are okay. As in, like, it makes perfect sense because this power here is work done over charge, and this one multiplied by charge over time. So what you just did was you went to calculate work done divided by time, which is fine. Yeah. So it's not unconventional. It's the exact same method actually.
Yeah, really good.
Yeah. But yeah, it's good to know that it is the same two methods. Yeah, it's the same two methods. Okay, we're done with this part 3 here. Do I need to do this one?
Also, let me go through the nuclear report.
Yeah, dude.
It's like
It's like I must use that word, no. I must use that word, then they finally click.
it's like the Rutherford goes scattering, right? Like when it like deflects from the right?
Uh-huh.
That's nuclear report.
Wait.
No,
No.
you should
Okay, fine. This one, does anybody need help in this? Nah? Okay. What? Part D, is it? Part E. Oh, this one. Oh, this is the other one. Okay, hang on. Wait. Okay. So you need to know this. No, guys, listen up. You need to know this. You need to know that if let's say one of them is 5 volts, right? One of them is 5 volts here, the other one is 5 volts here. They're in parallel, right? The total combination here is only 5 volts. No, okay. We're talking about this part here, or part E. Oh, internal resistance, huh? So yeah, you have to treat them as parallel. Yes, you have to reverse calculate and get the individual one.
Because it itself. Yeah. It is not. Like the answer sheet is very good. Huh? But it's not answer. Because what's the answer for the answer, right? And the effective results themselves.
Oh, there's a typo in answer key here. Yeah. No, it happens. No. Okay, so the idea is that we're trying to find this out, right? Okay, what's the total internal resistance that you calculated from the previous part? You calculated total internal resistance, right? 0.62 ohms, right? So what you're supposed to do is you wanna find out the total resistance of one of them. So this is 0.62 divided by 5.
Yeah.
All right, so you will get
8.06.
0.124 ohms. Hey, your calculator. Hey, someone sabo your calculator, is it? Hey, you notice? You know, is it the numbers at one here? Then someone go and rearrange all your keys. 0.124 ohms and 0.124 is equal to 1 over R plus 1 over R first, like that. Then you find R. You mean the answer key gave only 0.124 as a final answer? Oh. So like that lah. Yeah. You have to reverse calculate it. Yeah. No. This one. 0.124 is the parallel combination of two internal resistance. Yeah. Mm. Yes. You're supposed to EMF. Because that's for EMF. Bro, what?
No.
Okay. So EMF is 16, right? But when there's a current running, the current will waste voltage in the internal resistance, so the D only becomes 12. But they only want you to determine what's the EMF for one cell. So Yeah, voltmeter, ideal voltmeter, bro.
So like the TP is
When there's no current flowing, you can measure voltage.
Yes,
Oh.
yes.
I
No, wait. Wait. You take a battery, even if there's internal resistance, okay, and then you put an ideal voltmeter across it. So, like, we're gonna assume an ideal voltmeter. There's no current at all. Yeah, there's no current, so the I equals to 0, and then the voltmeter here will read. Let's say, for example, it reads 8 volts, for example. Okay, this will tell me that the EMF is legit volts. Hang on, then I go and connect this battery to a circuit like this. Okay, then I went to put the voltmeter here, and the voltmeter tells me that the reading here is now 7 volts. Right, so then they'll be like, oh, okay, how come just now I read 8 volts and then now it's 7 volts? Because now there is current flowing, right? And since there's current flowing, there'll be some wastage of voltage here, right? Some of the volts will be wasted at the internal resistance, right? And this voltmeter reads 7 volts, so how many volts is wasted there? 1 volt, right? Okay, it'll be like 1 volt across the internal resistance, right? Hang on. I'm now gonna ask you if I were to take this voltmeter and I connect it over to the other side here like this. What the reading of this voltmeter? 7 volts, still 7 volts, right? Still 7 volts. It's like you can't ever read the internal resistance voltage, voltage, right?
it's like the TP is just 7.
Yeah, the TP is 7 volts. That's right. Okay, right. You got this now? Okay, yeah. Okay, so that's good. Oh wow, this is fast. Question 2.
If you
Whoa, what the heck?
yeah,
What is a topic 12 question doing in question 2? Topic 12, man, this up right up to it. Topic 12. Okay, but this is a hybrid. This is topic 12, T12 and T no 9.
9. There's 7 later.
This is T12 and T9. Yeah, this is T12 and T9. Okay. Shall we do this? Yeah. Do I need to go? Should I go through this one? First one. Nuclear radius. Part 3, part 4, part 1. Anyone? Part 1, okay, part 1, okay. I just do a quick one. So what essentially are you doing? You've got a silicon nucleus, right? So this is Si30, right? Si30, and what we doing with it? We are, I mean, what are we doing with it? We are firing what at it? Electrons. We're firing electrons at it. Okay, wait, where's the alpha particle now? I heard you mention about alpha particle just now. I don't see alpha particles now. Part 3. Okay. Later on. Let's talk about the first one. So we're using electrons here. Alright. Then there's a screen here like this. There's a fluorescent screen, right? So electrons being fired at the particle, and then you get a fluorescent screen. Okay. Alright. Tell me what's happening here. What's the concept that's happening here? Huh? What's this thing? What's this? Is in my topic 12 notes, right? You can see the graph in my notes, which is the same graph in the question. But what is this? What is this concept here? You fire a beam of electrons at a nucleus. Huh? Diffraction. This is diffraction, right? Okay, but diffraction has 2 versions, right? What are the 2 versions? Okay, so you either dive through a single slit, or you diffract around an obstacle. This silicon nucleus is behaving like the opposite. So this is single obstacle diffraction. Okay, this is in topic. Technically, this is in topic 4 and topic 9 when they talk about diffraction, right? Diffraction, and this is the single obstacle diffraction. Right, single obstacle diffraction. You get what I mean? Okay. With a single obstacle diffraction. Shut up. The only time you learn about the definition of diffraction where they mention about the wave passing through a gap or across a obstacle and it diffracts. But you only really apply the single obstacle diffraction all the way at the end of topic 12. Right? You don't even use it in 4 or 9 anywhere. You only use this single obstacle diffraction all the way in topic 12. Right? So just to remind you of the thing. Hang on. But what happens to the pattern? How does the pattern of a single obstacle diffraction look like? Yeah. So the idea is that the pattern looks almost identical to a single slit pattern or single aperture pattern. How does a single aperture pattern look like? You know, if I try to jog your memory like this, right? So you have a aperture, you shine a laser beam, right, onto a screen. How does a pattern look like then? Right, you got a central maximum fringe here, then followed by a dark fringe with a gap, then another bright fringe, then another bright fringe, then another bright fringe. Right? This will be your single aperture diffraction. But for single aperture diffraction, what are the most important points on this pattern? The center and the first minimum here, right? The center and the first minimum here, like this. Okay? This is because the angle between the central max and the first minimum, theta, right? That's the angle, right? That you use in sine theta equals to 1.22 lambda over b. Right? This is the theta. Are we all clear on this so far? Okay, good, because the pattern for a single obstacle diffraction is the same. Same thing. You have a central maximum. Let's try to draw the screen here. Right, you will get a central maximum, right, followed by a minimum, then followed by some maximums on the outside like this. Okay? Right, so what's the most important points of this pattern for these electrons hitting the screen? The center and the first minimum. And therefore the angle between the center and the first minimum, this is theta. We're going to have to use this angle to help us calculate this equation. So sine theta equals, I think you have to use 1.22, right? No need. The answer key got say okay to use 1.22. Is there any mention? Okay for students to use 1.22? Comments? Never say they didn't use 1.22. A single obstacle is round, so technically you're supposed to use 1.22. You never say. Matures. Huh? The difference 1.22. Yeah. Oh, they gave the equation. Oh, what? Where? Oh, it's about 4 FM. Yeah, well, that's fine. That's fine. Yeah.
No, but if you show the wrong thing on answers, right? They just like leave it at 3.9. For example, it's 3.8, right? They leave it at 3.9. Answer the point. They say show. But do you need round off or do you need round off?
Yeah. No, just round off to 4 and say shown. Yeah. Okay, anyway, hey, hold up. So the equation for single obstacle diffraction is the same equation as single aperture. Right? I feel that it should be a 1.22 there. Right? I somehow remember some IB questions randomly also did include 1.22, so they're a bit inconsistent. Right? So I think it's fine if you put a 1.22. Your answer shouldn't be that far off. Right? Okay. Here's the thing. They did tell you the de Broglie wavelength of the electrons already, so you do have the lambda up there. Right? You need to get the theta from the graph. Right? Theta from the graph. And the theta should be what? What should the theta be? So you're looking for, hang on. So you're looking for this angle here, this one here. This angle here, like this. Right? Your central maxima is here, first minima is here. So anything else beyond that, don't care already, right? What first maxima, minima, nobody cares about that, right? So we only care about the central max and first minimum. This is the first minimum that's about. I don't know. My think my pencil is a bit off. Wait now. Oh. Say 18. 15, 16, 17, 18, right? 18 degrees, right? 18 degrees. 18 degrees here. So the theta from the minimum, from the central max to the first minimum is 18 degrees. Right? 18 degrees here, like this. Okay? Good. And therefore, oh, hang on, sorry, whoops. Therefore, B here, that's the diameter of your the obstacle. That will be B. That will be the diameter of your obstacle there. Right. So we use this to find B. Well, this is quite early though. Yeah, in the like question 2 and then suddenly a topic 12 thing. Huh.
They should show the I mean, the Aussies can read up and down. What the? Chinese people right there.
They read it upside down. Oh shit! Wait. This sounds like a good racist joke. What? So the Western reads from left to right, the Chinese reads from right to left, and the Aussies can read upside down. Okay. All right. Question 2 done. But then got requests for part 3 and part 4. Hang on, let me see first. Okay. So estimate using the result. So part 2 here, using the result from part 1, the nuclear radius of thorium-232, any data on thorium-232, you're supposed to use the Fermi's equation. You're supposed to use this R equals R naught, right? A to the power of 1/3. You're supposed to use this as a ratio, right? So R is proportional to A to the power 1/3. Okay. Right. So A is a nucleon number, mass number. So for thorium is 232. Yeah. So R of silicon over R of thorium is equals to, I can just say equals to, A of silicon to the power 1/3 and A of thorium to the power 1/3. Alright, so then you just make this the subject. Yeah, this one down here. Right, radius of thorium is subject, and then you find the answer. Like, I don't know about you, but do you feel that this sort of question is definitely a bit different from your prelims? Yeah, it's very different. This is the IB style. They love to do what you call ratio questions, right? Yeah. Which is also why I show you some IB questions sometimes, but I don't really use that to prepare for your prelims. Your prelims is a bit too basic, lah. Yeah.
You said prelims very hard.
So prelims, right? No. Your prelims, right? What they do is they the style of their questions, right? Okay, so a lot of the teachers in the IB side, right? They progress O level, A levels, then they shift over to IB for better life, you know. So they bring a lot of their O and A level type of style of questions along with them. And when they set the paper, they're setting it in the mindset of an O or A level student, teacher, right? Which will never set like this. But this is the IB style. You know what I mean? There's a very slight style difference to the questions. I would never do a question like this for the A level side. Like using ratio to go and find something like I would never do this for the A. I would never be able to do this for the A level side. It's a different thing. Angry. I'm even angry. Let's see how jammed it is. Whoa! Oh, almost got an accident. Oh, they touch. Oh, they're gonna fight. Yeah. Hey, no. Hey, y'all guys, stop looking at the girl outside. Oh my god. Joshua and Damien. Hang on. No, actually, the guy, he was away from the car. Then I think he got out of the car, but he forgot his car was, I think, in the drive. still in gear 1. Then the car was moving. Yeah. Yeah. Well, okay, fine. No fight. Show's over. Nothing to see here. Okay. All right. There we go. Come, let's finish this one here before we go for a toilet break. Suggest one reason why the beam of electrons is better for investigating the size of a nucleus than a beam of alpha particles of the same energy. Oh wow, okay. So you need to understand alpha particles of the same energy, all right, versus beam of electrons of the same energy. What is the? I want you. You need to. Okay lah. This comes with experience, right? So why would they be asking? Like I before I tell you the answer, I want you to think about why would they be even asking this question in the first place? Like, what's up with the difference of beam of electrons and alpha particles of the same energy? Like, what would be different? Charge. Okay, so based on the context of this question, the context of this question is using diffraction, right? Diffraction. So does charge play in diffraction?
Kind of a trust, like if you have.
But do you learn anything that deals with charge and diffraction? No, you don't. Huh? I mean, no. Does mass have we ever talked about mass affecting diffraction as well? Not. So you can. I think that the idea is you need to be able to catch very quickly that this will affect the de Broglie wavelength of the alpha particles.
Wait, sir. Wait, wouldn't the nucleus attract the electrons? It's negative and positive.
Yes. Right. So what Praveen said is correct. Nucleus does attract the electron. Okay. Which is why this pattern doesn't look like a perfect single slit pattern. A perfect single slit pattern is supposed to go all the way down to zero. The intensity of the electron is supposed to go all the way down to zero, but it doesn't because there's other things going on. But we'll still take this as the minimum. Yeah. Okay. But it doesn't deviate from the fact that there is still diffraction. There is still diffraction. Okay. De Broglie wavelength. I want you to compare lambda alpha and lambda e if both of them have the same energy. So we need to talk Ke equals to P squared over 2m, and we need to talk about lambda equals to H over P. For the same energy, which one has a greater momentum? The alpha particle will have a greater momentum, right? Because we can tell that P is equals to P squared equals to, well, at least 2m times Ke, right? And we have the same energy, so they have the same Ke. We're trying to say that they have the same Ke, right? So the alpha particle having more mass will have momentum. You can have the same Ke, but you have more momentum. Every alpha particle has a more momentum. So what happens when you have more momentum? What happens to lambda of the alpha particle? Huh? Smaller, right? Right. So it'll be smaller. And then based on this question, what's this question dealing with? Sine theta equals to? Huh? So alpha particle has more mass, right? So momentum alpha particle is bigger. If the momentum is bigger, then the alpha wavelength is shorter, right? So alpha wavelength is shorter. Then we need to consider the oh, wait No, but you see, they are not of the same velocity. We're saying they have the same Ke. Yeah, the same Ke. But I don't quite understand why they say alpha is bigger. I mean, if alpha is bigger, then it's even better for the alpha. The theta is bigger. You can measure it more clearly, right? The whole idea is that the lambda here will be very small. Smaller lambda, then smaller theta. Then smaller theta is hard to measure on the screen. What's the reasoning they gave? Shorter wavelength, so better resolution. Oh, they're not wrong.
They say I don't say like
What? What's both okay?
I think the answer he said electron wave function just going increases or something like that.
Oh, okay, okay. Something is wrong here. Yes. Yeah. No, hang on. I think I'm something wrong here. I think I'm more. I think I need to. Okay, I tell you what. I'll leave this question for later. But I need to figure out what this same energy mean. What? Yeah, it's not. It doesn't stick to the nuclear atom. You want to talk to Jalin about that? Wait, dude. Oh my. Wait. Wait. Doug, what the heck happened to you in camp? Doug, this is a nucleus, right? That's the electron, right? The electron is orbiting, right? It's not stuck to the nucleus firstly. Yes, what kind of attraction is that? Yeah, that's not nuclear. That's not a nuclear force.
If you fire electrons and the nuclear force, it's still attracted.
Yeah, that's what Bravin was asking. And I said that that's why the pattern is not a perfect single slit pattern. There's other things going on. Yeah, but anyway, this is the electrostatic force. The answer key says nuclear force. It's a strong nuclear force. Strong nuclear force is very short range, right? So only within the nucleus itself. Yeah. Okay. Yeah. What? Yeah, he's right. I mean, okay, no, hang on. So no, repulsion is still static. Okay, so this is the nucleus, okay? Right? This is the alpha particle here, like this, right? This is the 2 plus charge, this is positive charge as well, right? You say that the alpha particle goes close to the nucleus, okay? There's repulsion. Okay, so the one thing is there's repulsion, right? Then the strong nuclear force is an attractive force. Nuclear force is an attractive force. It's trying to attract it, right? It's a handcuff, right? Nuclear force is handcuff. So when the particle is very close to the nucleus, right? The scattering process or the scattering mechanism affected by this strong nuclear force, the strong attraction. Yeah. So it's not. So there are two different forces. The repulsion is due to electrostatic. Okay, charge. Correct. And then the other one is strong nuclear force is due to proximity. Strong nuclear force is just simply due to proximity, but how close? Close. What's the number for the closeness? Yeah, 10 to the power minus 15, correct. In the range of 10 to the power minus 15, right? Strong nuclear force. Yes, that's right. Sorry. But I like to explain something. Let me go and check on what they mean by this. Right, then I come back to you because I think I'm getting something wrong here.
This is not like the rule for those that they shoot the alpha particles like good. Then the go atom will either let the alpha particle pass through or like imitate back. Then you say that for this case is when you shoot a beam of electrons, when you shoot alpha particles into a nucleus, it will not get close enough to have nuclear repulsion effect, but you'll still rebel because it's like
But that's not answering the question at all. Yeah. That's not answering the question at all.
when you then
Like that doesn't explain why the electron is still better.
but you say electron is negative, but it won't be
It will be attracted
why?
because it's plus and minus. Let me go back and go and think about this. Okay, so there must be a reason why the answer key is saying whatever the answer key is saying. Okay, all right. But okay, so this one here, part 4. Let's talk about part 4. Part 4 is straight out from my notes here. Right, deviations from the Rutherford scattering. Right, this is straight out from the notes. So if you look at the notes, wait, where's nuclear recoil? I still don't see the word nuclear recoil. Oh, Hang on now. So the Rutherford scattering thing, right? You try to remember it. It's somewhere around here. This one. This is the one here. Okay, is that there's the part of the notes where you know this one here happens, right? The deviation happens. Okay, so outline why deviations from the scattering observed when high energy alpha particles are incident on the webcam.
Yeah, two max. Two. Those like those are 4 6. This is 4 months. This is 1 6.
This one how about in chemical physics?
Bro, this can be 8 mark question is 16 points. 32.
Alright, I owe you guys this one, so I'll come back to this one next time. Okay. Question 2, let's just finish up question 2. Oh, Feynman diagram, wow, that's early. I didn't do part I did. I did. I did. I was showing you this graph. I was telling you that the answer is here.
He gave us two different points, and like the part about like getting close and strong, it was only one point.
Okay.
So what do you put for other point?
What's the below this thing?
Don't bother. They like to use big words because they want to feel important. What does answer key say for this question? Sorry.
He says that nuclear was one of the points. Then they said nuclear recoil occurs in significant penetration in nucleus, and incident particles are relatively small. So they say two of them small.
Oh yeah.
Let me see again.
There's nothing. Okay.
Okay.
Oh yeah.
I guess you can add in the slight penetration then. Yeah. I guess you can add in the slight penetration part. No, because the alpha particle got absorbed into the like it got partially absorbed, or rather temporarily absorbed into the nucleus. It got temporarily absorbed in the nucleus.
Oh.
Yeah. So it's like based on my notes, then maybe you have to add in this other part, right? This strong nuclear force to take effect, and then the alpha particle gets absorbed into the nucleus. Yeah, something like that. But it's not even a permanent thing. It gets temporarily absorbed only. It's a temporarily absorbed thing. Yeah. Yep, that's annoying. Yeah, that will be the yeah. Yeah, and the alpha particle gets temporarily absorbed in the nucleus. Yeah. Huh? Why are the electrons deflected by it? Is it? I'm sorry.
Yeah, it's in the why if it's and you get it completely.
So I think to really answer that question, you have to think of like Nerf guns with blue tag on their fronts, and then you just fire a lot of like Nerf gun bullets at the target. So while some of them get, the others would like deviate, they bounce off lah, yeah, bounce off. So it does bounce off, but it's not a It's not 100%. It's not 100% deflected. It's not 100% absorbed. Yeah. Yeah, that's right. Yes. Yeah, just close enough. Nuclear force is attractive, so it's kind of like, you know, it absorbs. Yeah, it absorbs the alpha particle. Like try to assimilate it, like a white blood cell and a pathogen. That's all I can say. Sometimes the answer keys are a bit weird, but yeah. Okay. Can I do part B? Let me finish up part B and then go for a toilet break. Come on. Let's do this. Do I need to do? Nuclear reaction, okay. Payment diagram, okay. Wow, three marks for this one. Yeah. Nice. Time axis is on the y-axis. Right, so always remember, if you get very confused, just remember to draw the before after, right, in pencil, right, before and after. Determine the emissions of quark confinement for this situation, where you try to transfer energy to a hadron in an attempt to separate its quark. Will happen, right? Basically, you'll form a quark anti-quark pair of mesons, right? I think you have to write it in that much detail, which is also in my notes. No, in topic 7. Sorry. Yeah. This quark confinement is in topic 7. Oh, the answer key was that vague?
Yeah.
Oh, okay. Well, I mean, yeah, you can say that the quarks cannot be isolated, and therefore the energy will be converted into other quarks paired to the quark itself. Like, or no, or rather, you can say it forms quark pairs. Yeah. Okay, so quark confinement is a theory. Quark confinement is a theory. The theory, in simple words, just means that quarks cannot be isolated. The word quark confinement is a theory, but it means that quarks cannot be isolated, right? So the whole idea is I'm trying to isolate the quarks here. I put in energy to try to break them apart, right? So what does quark confinement tell us? What will happen eventually based on this action, right? Based on action, quark confinement tells us that the energy that you put in will be used to be created, will be used to create, or will become, the energy will become other quarks that is paired, right, or pairs of quarks, right, and isolated quarks. Yeah.
Let's say the energy is like energy result as fraction of another meson.
Yeah, you can say that. Yeah.
The energy result is fraction of another meson anti-meson. Oh.
But I think you have to write down somewhere that the quarks are not isolated.
Oh.
Yeah. Yeah. You have to write down specifically that quark will not be isolated.
Wait, meson is what?
Meson is a two quarks. But meson, specifically meson, is a one quark, one anti-quark.
Also, meson anti-meson pair is what? What is that?
So the energy that's being produced, right? The energy that's being used to produce these two. So this will be a Q and anti-Q, and this one will be an anti-Q and Q. So this is the meson, and this is the anti-meson. What? You just said, is there a name for the sausages?
Yeah.
For the meson? No. As in, like, you don't need to know specifically what kind of meson is being produced or anti-meson is being produced. It could be random, actually. And bratwurst. Okay. Yeah. Okay. So yeah. So there's an anti-quark and quark in each of the meson or anti-meson pair. but the meson and anti-meson. Yeah, there's two of it. Actually, the energy will produce 2 extra quarks.
So quarks will not be
Hmm.
more.
Yes.
Oh.
Yes.
Oh, makes sense. Hadron is 3 of it.
Yes.
And meson is 2 of it. 1 anti and 1 normal.
Yes. Yes.
Optimus Prime is the machine.
What? Okay. Last part of 2. Standard model accepted by many scientists before observation of model.
This is so stupid.
This is nature of science, which I have never gone through before. I don't bother. Or is it TOK or something like that? Like, yeah.
Holy shit, this was my WEP to satisfy intellectual curiosity. That's my intellectual. What's your how do you spell intellectual?
Not very intellectual.
How the hell are they?
Intellectual. Okay.
That is correct. Intellectual.
Wait. What's the answer key for this?
All can be revised.
What models can be revised?
Information you can advance. They say models need testing, new information may change models, new technology may bring new information.
And you identify your intellectual curiosity.
Okay. That's fine. Okay. Actually, the best example for this will be I think right in the olden days I would think that this sounds a lot like conventional current. The scientific model for electrical current was accepted like a long time ago, 100 200 years ago, that current flows from plus to minus. But they continue to research it and then realize that it's actually the electrons that flow, but they messed up already. Yeah, so they call it a conventional current. Yeah, so new models from new technologies, right? Yeah, so revised models. So electron flow versus conventional current. Okay, but I have no expertise in this nature of science or TOK questions. It's only about like maybe 2 or 3 marks in the entire paper. I really okay, model answer is intellectual curiosity. Oh, those are very big words, dude. Okay, take a 5-minute toilet break. I'll come back and I'll do the topic 2 and topic 5. Please don't break my tables. For sparing errors. Sparing errors. Sparing errors. How many L's are there in spelling errors? Sparing errors. Oh yeah, very. You know why? Because it's a leading question. It gives you chance for the next part. They ask you show, right? If you couldn't do the first one, you can just take the answer from the first one and try to do the second one. Then the IB model has failed you. Huh? What?
Sam, have you been to the club?
Yes.
You know the dog store there? The dog day there?
No.
The one with the doggy pool there.
Where the heck are you in Turf Club?
Have you never been to the dog?
Okay, I gone to the Turf Club, the main stage, the grandstand.
What?
But what's there to eat? I don't know. He thinks it's a Turf Club. Oh my god, can you be more specific? If not everyone end up with crunchy. Dude, that doesn't help. You have to say it's buka. $10 on Hail Mary. $10 on Hail Mary. You start betting. 18 rays also can go Turf Club, right?
Oh shit.
Huh, what? How much is it per person?
But they're selling $4 drinks. Where you can find $4 drinks in Singapore?
No idea. You smuggling liquor, is it?
No, we're selling it plus. We're not making any money from
This
it's gonna be a big
no need lah. Walao, you ask for need lah.
double
Wait. I just got this bad image in my mind that you're gonna be partying on the grass.
Oh, it's not grass.
Yeah.
It's a mix of all. But then we're gonna get like.
Is it at the seats there? Is it at the seats there? The grandstand, the seats. I'm very confused. So it's not at the grandstand, is it? At the grandstand.
No.
It's not at the grandstand.
You know, like the.
Uh-huh. On the right or the left? Is it where Valentino's is? Is it where the football the football pitches are?
You should book out a pitch. Drunk FIFA, drunk edition. Skill challenges. Yellow card. You have to buy 4 drinks for everyone here. Yeah, actually, you just what they did.
How was the logistics gonna be like? How many bottles are you gonna bring there?
All our stuff is all external vendors. It's like some bartender.
But how much? What's the number you tell the bartenders? Like
We're aiming for 100 people.
what if other school students join in?
So then we get our seats, number of tickets. So then the place is a restaurant already. So like we can like ask them for their.
Wait, it's a restaurant,
Yeah. It's not hot.
Hey, please don't trash the restaurant, man. I got a very bad feeling. Hey, you better keep all the furniture somewhere, you know. Yeah.
And then we're getting.
And then take the glass up.
We're getting insurance.
Take the glass. No, you know glass panels, right? Take it out, man. Seriously, you don't want it to shatter. And then, yeah, man.
We're making everyone sign waiver, whatever.
Okay.
We're multiple layers.
Okay.
They're all protected, but how do we protect the restaurant? It's because you guys tend to run more than once, right? Like you guys tend to run.
Yeah.
The danger is right. No matter whether or not you're covered, if I get a bodyguard, like you guys stop on me, right? If something happens and you guys clean up the mess, right? People go around and talk. I saw you guys harassed at the party, right?
I don't know. We kick them out. We're very.
Yeah.
It happens everywhere in Singapore.
No, he's right. He's right. He's right. He's not wrong. He's right.
It doesn't matter like what happens there.
No. Hang on. So are you trying to give Zook out a run for their money? That's the thing.
No.
You know me?
It's a different crowd.
Different crowd. Wow. Hey, if you're gonna keep attracting all these like 18, 19, right? Like 18, 19. Yeah, the 18, 19s, right? You better watch out for old updates, seriously. Yeah. Those people, those 40-something-year-old ones. Let me just tell you something, okay? A 40-something-year-old guy goes to these kind of parties, right? Chances are they're not there to look for girls, Yeah. I'm serious, man. The chances are they're not out there for guys, man. Just be very careful, man. Yeah.
At least it was get 3 bounces, but then we're getting like 5.
Wow.
We're
Okay.
like doubling our bounces.
Yeah, there's security. Yeah.
Bouncers for sale.
This guy is trying to do the Burning Man for Southeast Asia. You can do the Burning Man for Southeast Asia. You can start like attracting all the like the regional party goers and all that also.
We're just making sure that our first one.
Like go to Lim Chu Kang, set up Burning Man. But Lim Chu Kang is a cemetery, so okay. Right, just a quick one. I think the last time I went through was half MB square, half MB square. I think I mentioned this. All right. I'm going back to the revision now. Then we have the work done in springs. I don't know whether you remember this, but this is a thing. Please read this. Okay. So work done is equal to half kx squared, and additional work done should be half kx squared minus half kx1 squared. Right, like this.
This is the prelim question.
Huh?
This is the prelim question.
Really?
Yeah, I think. Oh, I didn't know this. Wait, really? But I don't get it right.
Okay, fine. Yeah, hook law. Yeah, hook law. This is hook law. Okay, all right then. Don't forget. Yes. Uh-huh. Yeah. Okay. Sorry, I don't quite understand what the context of the question is. Oh, they. So if you have if you have this horizontal spring mass system, that is, okay, horizontal spring mass system. So if it's a horizontal spring mass at equilibrium, what's the EP stored inside the spring? If it's at equilibrium, what's the EP here? 0. If it's at equilibrium, there's no EP, right? Horizontal spring mass system, okay? And then, of course, it will oscillate back and forth. As it oscillates back and forth, so there will be extension, right? There'll be extension here, and then there'll be compression here, like this, right? This is a horizontal spring mass system. The spring is always extendable and compressible. So, hang on, the amount of energy, the amount of maximum EP that you can store inside this thing, right? Max EP, right? Max EP basically half kx squared, right? Right, according to what this equation is, right? Half kx squared. But then also at the same time, you also recall that for SHM, right? SHM, the equation for the equation for PE, right? The equation PE is basically total energy minus KE, right? Total energy minus KE, and then you get something that looks like half M omega square x squared, something like that, right? Okay, good so far. Yeah. So then of course you can also ask like, okay, so what's the relationship between this and that, right? What's the relationship between the equation, the spring equation, and the equation? They're the same. We're gonna call this x naught though, because we need to find out what's the maximum EP, right? The maximum EP and the maximum PE here, right, is based on the amplitude as well. And yeah, So if you compare coefficients, what's the same here? Compare coefficient. What's the same between the two equations? You have your this one and this one. What's or rather, yeah, I mean x naught squared is the same, but so what is equals to what? K equals to m omega squared. Yeah, compare coefficient k equals to m omega squared, right? But let's expand this whole thing out, man. K equals to like this is 2 pi over t squared. Oh, you know what? Yeah, then you how about you just rearrange it? Suddenly t equals to 2 pi square root m over k, which is your topic 9 equation. Yeah, so yeah, the that's where it ties in, I suppose. Yeah. But if it's a vertical spring, yes. I mean, that's what elastic potential energy is. Potential energy, yeah. The KEP and TE, yeah. There's only 3 types of energy that you need to worry about, right? Kinetic, total, and potential. But yeah, this is not so straightforward for vertical spring mass system, huh? For vertical spring mass is different. I think this is the question you were asking, right, Joshua? Vertical spring system. Okay, can I close this?
Yeah.
Oh, all right. Yeah, just go ahead and write down whatever you need first. We good? And all right. So vertical spring mass system is going to be a much more painful process, right? So we must understand that for vertical spring mass, when it's vertical, right, at equilibrium, right, at equilibrium, it means when this object is hanging off its equilibrium. Do you agree that this thing has some EP? As in no, as in like let's just hanging here, like haven't oscillate yet. Like is there some EP at this position? Yeah, there will be because there will be some stretching, right? There'll be some stretching. So for example, it stretches by, let's say, like E. I like to use E when it comes to vertical, right? Because there's a bit of extension, right, from the original length of the spring, right? L naught. There's a bit of extension, right? Okay. But what is the X? What is the X here? What's the displacement here? What is the displacement at this position? X is 0, right? The X is 0. There's no displacement at all, right? And then what happens if you were to take this mass and you pull it down by a certain X like this, right? And then it will oscillate, right? And you let go, it will oscillate. So what will be the amplitude of oscillation? Yeah, it will be X. It will be whatever you put it down by, right? The amplitude of this oscillation will be X. But let's say we look at the most bottom position, right? Let's look at the most bottom position here, right? What is the energy stored in the spring then at the most bottom position? Like, how do you express the equation for it then? It'll be half k e plus x naught squared. Yeah, because it's e plus x naught, right? X naught is from the equilibrium, e is to the equilibrium. You get what I mean? Right? So yeah. Yep.
So E is from like when it's at the spring is just no extension.
Yeah.
Then when you put a weight extends E.
When you pull the mass,
Then when you pull it down.
No, wait. E is when you hang it there. Yeah, when it's just hanging there on its own. Yeah, when it's just hanging there on its own, that's E, right? There's a bit of extension. So there's already some EP, but then when you go and when you go and extend it further, right? Then the total EP of the entire system will be half K times E plus X naught squared. Okay. But here's the thing: this might not represent the SHM equations. The SHM what call it energy, right? PE might not be this value, PE, TE, KE. It won't be, right? Because here's the thing, that there is a difference from the horizontal spring mass system. This one will be EP, right, when it's at the bottom, because you have to include the extension at the equilibrium position. But if you're looking at the SHM, the P won't be, it will not be this equation here, right? Yeah, unless you assume a very nice curve that goes like that and like this, right, where the total energy is the maximum EP. Then yes, right? Then yes, you can say that this equation here is the same as this one here, right? But they usually will not try to test you for vertical spring mass system, okay? Right? For the IB, they will avoid trying to test you for the vertical spring mass system because it's very confusing. Are we okay on this? Can? All right. Let's continue on this one here, power. Right, I think there's only one of the equations that I want to be refreshed on, which is P equals FV. You may have to show this. You may have to show that how this P equals FV comes about. All right, and I think we already more or less did one of the questions, so we know about this. So when the car is moving at a certain speed, there's a certain driving force. Okay, and if they tell you that it's a constant speed, then the driving force is equal to the drag. Right, constant speed, constant speed means that the driving force is equal to the drag. You understand this? Okay. I give you a scenario. Let's say the driving force of a car is 4,000 newtons, and the constant speed here is 2 meters per second. Right, it's very slow. Right, 2 meters per second. What is the drag force? The drag force 4,000, right? Okay. But then how about this? I ask you a separate question. I ask you what's the rate of heat and sound produced? Right, rate of heat and sound produced. I try to twist the question a bit. Like, what's the rate of heat and sound produced? It's just 4,000 times 2, right? Which means 8,000 watts. Right, rate of heat and sound produced. Huh?
How do you get that?
Yeah. So at constant speed, driving force of the car, whatever the driving force it has, is simply used to overcome drag force, right? There is no increase in E. So whatever the power of the engine is, which is 1,000 times 2, force times velocity, that will be the power at which you're losing energy as well. Yeah, drag. Yeah, I mean when you do work against drag, you will get heat and sound.
Oh, okay.
Heat and sound. It's a truck. Efficiency, okay? Right. I don't know. Just want to make sure that for the last time ever, just remember that efficiency is full over total. Right? Useful over total. So which means that sometimes you need to figure out what is useful, what is not useful. Right? Yes. Let's say there's a motor, right? And the motor is lifting up a mass, right? For example, lifting up a mass. Okay, let's just throw a question in 5 kg lifted up by 8 meters. Right? Lifted up by 8 meters. And it does it in 2 seconds, right? So it lifts up a 5 kg mass by 8 meters in 2 seconds. Okay. right? And I tell you that the power input of the into the motor is 100 watts, for example. Can you tell me what's the efficiency of the motor? Yeah, there we go. Power input into the motor is 100 watts, right? And the motor is able to lift up this mass of 5 kg, 8 meters in 2 seconds. So what's the efficiency of this one? Huh? I think so. I think so. Really? So the power to raise this thing up is mgh over time, right? Right. Mgh is 8 times 5 times 10, 9.81 ah. Oh, whoops. Yeah. So the power is too little. Sorry. I'm gonna do 500 watts. How about that? 100 watts. So 50 is 400 over 200 watts, right? 200 watts. Yeah. So the huh?
Isn't 5 equals to mg because you get this 5 kg? Oh, wait, no.
5 kg is mass, huh? Right? Yeah. Right. So mgh, yeah, divided by 200 watts, yeah. Okay. Yes. All right. So I give the 100 watts a bit too small at first. All right. So efficiency here will be 200 useful over 500, and then that will be your efficiency in percentage will be, huh? 40%. Right. So the efficiency of this motor is 40%. Okay. So what happened to the 60%? Heat and sound, right? The other 60% became heat and sound, right? As the motor is turning, right? So heat and sound. Okay, so there we go. That will be the questions here, right? You understand these things, very basic stuff, but you really need to go and do more practice, right? Because I can't possibly give you the whole, like, range of scenarios, right? Okay, I want to start on topic 5. I know I only got a few minutes left, right? But I want to start on topic 5. I want to continue on Tuesday and Wednesday, okay? Right. Topic 5. Anybody who does not have the notes at all, just like, yeah. Do you not have the notes before this? No. Okay, hang on. Only one guy. Okay. Topic 5. Now, topic 5. It's a very long topic. I think some of you who came last year also know about this, right? It's a very long topic. But I will try to break it down into a few parts. There will be some parts which will definitely take me too long to explain everything in detail. So for those parts, I will encourage you to request the videos from me, right? I will just send you the clips where I explain certain things, like for example, basic Sec 3, Sec 4 circuitry, which I would encourage those who have never attended this sort of lesson to go and watch it first, right? But part 1 wouldn't be that at all. Part one is a lot of it is about the electric fields. Okay, it's about electric fields. Part 1 is about electric fields. So if you really need a bit of guidance as to what topic 5 is broken up into, please look at your syllabus guide. Right, so let's look at part 1 first, right? 5 part 1. Okay, 5 part 1 here. Right, so we talk about forces, fields, Coulomb's law, charge carriers in the metal, right? Then later on about drift speed of charge carriers, drift speed, current potential. So it's like there's 2 parts of 5.1. 5.1 is split into 2 parts. These 2 parts here, right? First part is called static electricity. Static electricity. Second part here would be current of electricity, right? Current of electricity, COE. Okay. These two were two separate chapters in Sec 3, Sec 4. Right? There was electricity, and then there was the current of electricity. In Sec 4, you learn quite a bit about static electricity. Like for example, there's a plus charge and a minus charge, for example, and they ask you to draw a few lines between the two of them. Right? Draw a few lines between the two of them. So we had to draw a few lines that look like this, like that, like that. Right? So you remember all this from secondary school, right? Okay. So these are all the stuff that you learn from secondary school. Right? And which is what you also learn now as well. Okay. But the difference is this. We know that these two charges will attract each other, right? We know that these two charges will attract each other. So then we need to ask ourselves, how do I calculate the force that attracts each other? What's the equation? Right, it will be K Q1 Q2 over R squared. What does R stand for?
Distance between the center of each
Right.
sphere.
Distance between the centers, right? This will be the R. Okay. Then always remember force comes with the square. Force comes with the square. Okay? Can? Alright. Now, how about potential here? How about electric potential? You know the voltage, right? Potential is voltage, right? How about potential? I mean, yeah, there's an equation for potential. Okay, there's an equation for potential. But honestly speaking, if you're revising topic 5, potential doesn't appear here at all. Yeah, it's in topic 10. Potential for point charge is in topic 10, right? You want, you can go there and then you refer there, right? But you know, if I'm going to do topic 5 as a revision, I will not to talk about potential here. Okay, so for the first part of 5.1 is really strictly all about static electricity. Okay, right. But there is one thing that I need to go through. It's called field strength. Okay, so after we calculated force, now we have to find E field strength, and then don't forget E stands for E field strength, right? E field strength. Okay, so force, the force that you calculated just now, right? This is the force by the minus charge acting on the plus charge. The other force is by the plus charge acting on the minus charge. So you get what I mean, right? So there's a you know, you're using the equation for the forces between the two charges. But when you use E field strength, right? When you use E field strength, when trying to calculate E field strength, you're not trying to calculate the E field strength, right, acting on a charge like this. You're not calculating that at all. In fact, what you're calculating is, I give you a random point, right? Then what is the E field strength there, right? So E field strength, the usage of the equation or the usage of the concept of E field strength is like this. I give you a random point. Tell me what's the E field strength there. And on top of that, you still need to do what? You need to find out what? You need to find out E field from one charge. You need to find out for the E field another charge, and you do a vector sum because E field strength is a vector. So I think you all know that you have to find this. You have to find this, and then you have to find the resultant here. Okay. So E field strength, this arrow here points away from the plus charge. Right? Why? Right? It's because E field strength, electric field strength, the definition, right, is defined based on a small positive test charge. Okay, is defined based on a small positive test charge, right? You don't understand what this statement means, right? Just a very, very simple idea is this. It's as though you put a plus charge here, as though it's an imaginary plus charge being placed across here, right? That means you imagine placing a small little charge there like this, And then you ask yourself, so what's the direction of experience from this plus charge? This way. If the plus charge is there, the direction of force acting on this plus charge from here. This way, right? So then we need to find out what's the net field strength. The net field strength will be in the middle here. Are we okay on this? So far? Understand this so far? Okay. Right. Hang on. Let's what I'll do now is I'll dial it back a bit. I'll ask you now. Give me the equation for this E field strength at this point. K Q over R squared. There's a square, right? E field strength, there's a square, okay? No, E field strength, there's a square. Because E field strength is a force per unit charge, right? E field strength, E is force per unit charge, right? That's the definition, force per unit charge. So it's basically just the force equation divided by one of the charges. What's this Q here? Right, the Q of the charge here. What's the R? Distance from here to here, right? Distance from here to here. This would be R, right? Then you do the same for the other charge, right? If you bring back the other charge minus charge here, you do the same thing here, right? And you have to do a vector sum. So this only comes out MCQ. It will just ask you to indicate where's the direction of the net field strength at that point there, at the point cross, blue cross there. Okay? Are we talking about energy? Are we talking about potential energy? Are we talking about potential? No, not at all. We're just simply talking about force. We're just talking about the amount of force per unit charge at some random point. Okay, okay, good. So then the next thing I need you to recall is this. I did mention one thing before. What is E field strength also known as? Okay, E field strength is also known as potential gradient, but I don't want to talk potential gradient now because I'm not revising topic 10 today, right? So E field strength is E field lines. Right? E field strength is E field lines. So if I ask you, okay, can you actually draw the E field lines again? Right? Can you draw the E field lines? The E field lines will look like this, right? This is what we drew in secondary 3 and 4. Like that. Okay? Right. How about that line that passes through the blue cross there? So what E field at that point? Tangent to the curve. Right? This is the E net. So what I'm trying to show you is that E field strength, if you continue drawing like lines like this, right? Then the E field strength represents E field lines. Right? At any point, at any random point, it's always a tangent to the line. Right? Of course, if it's a straight line, it's a straight line like this. Right? This is the E here, this is the E here, this is the E there, this is the E here. E field strength is E field lines. But the next thing that some students get confused by is this. How about just now the force, the equation, the F equals to KQ over R squared? What does this equation got to do with this E field lines? Hang on, no, this is vector also. What is this equation got to do with these E field lines? Right? My answer to you is nothing. Okay? Right? This equation helps you calculate what? The force that acts on the charges. Right? The force that acts on the charges. But this equation, E equals to KQ over R squared, this equation helps you to calculate the field that's between the charges. Right? This equation helps you calculate all green lines here. Right? All the green lines here. But this equation, right, the force equation helps you calculate the force that's acting on the charges themselves. Right? This is the part where students get very confused between the two, right? So maybe if this you to compartmentalize the thing, then hopefully it works this way. Are we okay so far? Okay, yeah? So when we are calculating this E, right, random points are between the charges, right? Okay? It can be here, it can be here, it can be here, it can be anywhere. Right? It can be anywhere. Right? Anywhere. What this equation helps you calculate is the E field strength that exists between the two charges in the region, or maybe even beyond, right? Around the charges, the E field around the charges. But this equation, when you use this equation, F equals to KQQ over R squared, this equation helps you calculate the forces as acting on the charge itself. Yeah. Okay, huh? Right, so technically speaking, these two equations don't really have anything to do with each other within this picture.
So like all the tangents of all every tangent of everything is
Yes. Everything E is the E net at point. At this 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 point. Every one of these pink color arrows is the E net at that point in this region. We okay so far? Yes? Okay, good. Then let's talk about now point. Let's talk about now point. Okay? But here's the other thing. Is now point zero potential? Does now point mean zero potential? Now point does not mean zero potential. Right? Now point does not mean zero potential. In fact, I don't want to talk about potential because potential is topic 10. Alright, so topic 10. Okay, so I don't want to talk about potential. But yeah, now point. Now point means now point means the field strength is zero. Right? Net field strength is zero, sorry. So now point means that the E net equals zero. So again, you need to try to recall when will be the times where E net is zero. Right? When will be the times when E net is zero? Okay? Right? Yeah. So we're gonna do this 5 coulombs, get it positive 2, like we put two positive sides here. Right? Where's the null point? The null point will exist here, right? Will exist there, but why? Inwards, why? The field strength from the +5 points where? Points to the right. Right, so this is the E of the +5, and the E of the +2, sorry, going left, the E is of the +2, like this, right? Where the null point exists, these two E field strengths are the same, right? They cancel each other out, right? But am I talking force here? Am I using the F equals to KQQ over R squared equation? No. The F equals to KQ is to calculate the force acting on the charges. If I ask you, so what's the repulsion acting on the charge? Then okay, by all means go and use the F equals to KQQ over R squared. But we're not doing that here. We're asking you where's the null point, right? The null point is a region within the charge where the field strength in this region is zero. So looking at the E field strength equation.
Why don't you use force? Why don't you use that? Then it's like you want plus one.
No. Positive dash charge is not 1 coulomb. Positive dash 1 coulomb is a very, very big amount of charge. Yeah, no.
So just use equal.
Yeah. Always, yeah. You always use E equals to E. Yeah. So
supposed to use F.
somehow
no. Oh, but no, that doesn't sound too right. Oh my god, no. Okay, wait, hang on. I want to finish this up. So what's the equation for this one? This will be K plus 2 over, I'm going to call this is R2 here, R2 squared, right? And then I'm going to call the right left side one R1. And this is equals to K plus 5 over R1 squared. Right, that's where your null point is. Your null point shows you that these two are equal to each other, right? Again, this is about the, this is not a repulsion. This is not talking about the repulsion between the two charges. The repulsion between the two charges is a totally entirely different thing. All right. So it's a force acting on the charges, yes, but we're not dealing with that force. We're dealing with the field within the two charges. Yes. Firstly, that's gravitation.
I just give this for him. It works.
Okay, what you're saying, so the idea is, if you assume there's a positive dash charge there, all right, then the amount of force that it experiences is k plus 2 times q of that. That means you're introducing a third dash charge here, like a third charge here, right? Yeah. So the thing has out, so basically becomes field strength. Field strength, okay? Field strength, okay? Field strength. Yeah. No, I introduced both concepts. Yeah, I introduced both concepts. Any questions so far? Okay, again, still not talking about potential, right? I'm not referring to potential, right? Of course, now we're gonna do a speed run and we're gonna identify where all the null points are. Plus, this is plus 5, hang on, this is plus 5, plus 2, plus 5, minus 2, this is plus 5, minus 5. Okay, come. All right, speed run. Where's the num for the first one? Right in the middle. Right. Next one. Right, closer to this one. Right one. Behind the minus 2. Null point here. One. All right. Last one. No null point within the region. What? One is positive. One is negative. Both equal magnitude. No null point in the region. Null point on E field strength is 0 at infinity, so not within the region. Okay, good. Yeah. All right. Am I talking about potential? No, I'm not talking about potential, so don't confuse this with potential. Okay. All right. Okay, then I'll finish off today's lesson with one last thing. I got 3 more minutes. All right, I finish off today's lesson with one last thing. Parallel plates. Oh yes. Yes, that's why there's no null point. Null point means that the field is 0, right? So if let's say you look at the last one here, the plus 5 is pointing right. The E field from plus 5 is pointing right. The E field for the minus 5 is also pointing right. They add up. So it's not 0. The E net is double. Yeah. But it's not the strongest there. It's not the strongest here, okay? In the middle, it's not the strongest. It's just that because it depends on the distance away from the charges. Right? It depends on the distance away from the charges. Right? It's just that it's not 0. I'm just trying to show you it's not 0. Positive charge needs to be bigger than the negative charge, or the negative charge bigger than the uneven charges. Then the null point will be on the outside, and it will be nearer the weaker charge. Like this. Okay? Yeah. Now, another thing about these things, the graph drawing, right? Which is the graph drawing. Let's say, for example, you've got a plus charge here and a minus charge here, and they ask you to draw the graphs. E field strength between the two of them. The E field strength between the two of them. Yes, you need to learn how to draw the graphs. Right. So, yeah. Okay, you know what? I'll do this the plus 5 and minus 5 one. Plus 5 minus 5. All right. So equal. Okay, and I ask you to draw the graph. The graph will look like this. Right. The E field strength.
E field strength is 0.
No. Wait. Inside what? Inside the sphere. Yes. E field strength inside the sphere is 0. Sorry, it's a bit wonky. Hey, how come my curve not smooth here? Hey, why lopsided one? Okay, there we go. I have to use what? Procreate. Procreate sounds so weird. Isn't Isn't procreation like creating babies? Okay, but In any case, you got to remember that inside the charge, the E field strength is 0, right? Inside the charge, E field strength 0. Okay, all right. A few more weird things, guys. A few more weird things for field lines. I'm not talking about parallel plates. Maybe I'll just end off with spherical charges, right? I'm not talking about parallel plates yet. Okay, so maybe I end off a few more weird things about spherical charges, huh? So this is you drawing the E field graph for the two charges. Then sometimes you have the they ask you to draw the E field lines. Wait, E field lines. Okay, E field lines. Sometimes they ask you to draw the E field lines. Can I close this now?
No.
What?
Yes.
Okay. Let's say I ask you +5 and -2, right? Can you draw the E field lines between the two? Okay. Yes. Right. Like that. Okay. There you go. Right. This one here. Like this. Right. What am I trying to show here? Stronger charge, weaker charge. Right. Positive, negative. More field lines coming from the stronger charge. Less field lines coming from the weaker charge. Right. Yeah. There you go. Right. There's no need to show null point, but the null point is here. Right. Where the butt crack is.
Oh. How the equal graph system?
I just drew it.
For the +5.
Oh, +5 -2. Okay, hang on. So okay, you know what? Yeah, I rarely actually draw both at the same time, so I'm gonna draw both for Mateo. Hang on. So we have a +5 here and a -2 here. Then there will be the E field graph, ER graph. Right, again, dotted line on the surface, dotted line on the surface. The graph will look like this, bro. It'll be like this. Eh?
What?
Just now draw plus and minus, right? Yeah. Okay. Come here. Yeah, you look down here. Okay. I cannot take it, no. Okay, like this. Okay, something like that. But it's still 0 in the middle. Right, something like this. So it's slightly shifted to the side, but it does not touch 0. Right, the center region doesn't touch 0. The problem is this. Okay, what I want to show you now is this. Okay, actually, it's a good thing that he brought this up. So these are the field lines between the charges. E field lines are E field strength lines, but this is the graph for the E field line. This graph, right? This graph is only for the center one here. This red color graph is technically only for this one here only. This one in the center here.
We don't want to put null point in the graph.
You don't. If you want to put the null point on this graph, right, you have to draw it behind the this -2 charge here.
Look like the go down.
It will probably cut somewhere here. Maybe somewhere there. Yeah. What? Sorry? Don't worry. There's never been a question where they ask you to draw the null point. But you know, if they ask you to indicate, you just need to draw a cross. It's there. Yeah, it's there. They won't ask you to draw the shape of the graph up beyond the -2. Yeah. Okay. I got to run. All right. I will continue this on Tuesday, Wednesday. Right. But Tuesday, Wednesday, there will be like I'll start off with this revision, then I'll go back into paper 2 again. But I'll be doing that, right? So revision paper, revision paper, revision paper. Thank you very much. Bye bye. Bye bye.